When I say roller coaster problem, although we will get to roller coasters, I want to point out that the problems we're really talking about are problems that tend to have three pieces that kind of come together for these questions. So what I'm really starting with here is what's not going to look like a roller coaster problem, but you'll understand why I classify it the same way after we talk for a few minutes. So assume I have like a box on a string, maybe 0.5 kilograms and 1.2 meters, and it's attached to a pivot point here so that I could release the box. And when I do, the box will swing downwards until it has reached its lowest point, say right down here. But when it reaches this point, it's clearly going to have some velocity in that direction. Now, this doesn't look like a roller coaster problem, but when I say roller coaster problem, what I'm really talking about is a problem that might ask you something that requires a combination of things to solve. For example, I would be interested in you telling me how much tension there is in the cable. Now, the reason I call these roller coaster questions is because we will have similar questions that involve roller coaster tracks. But this problem and the roller coaster problem are essentially the same in that they bring three pieces of information together. First, at their heart, you should clearly see that there is conservation of energy as a big part of what I'm asking you to do. If for no other reason, it should be clear that the object has gravitational potential energy here based on its height above the lowest point. Remember, anytime an object changes height, you should consider if energy is a reliable thing to count on in considering the problem. Do me a favor though, before I go on any further, put a yes or a no in the participant window if you could tell me what the height is. Okay, so, I was expecting to see about that kind of split with a few people being unable to. I'm not calling you out, it's 1.2 meters. The idea here is that they won't necessarily give you the height, but they would tell you, of course, that the object's maybe on a string. Well, if it's 1.2 meters from the pivot point to the object, that means it's going to be 1.2 meters in this direction as well. Unless, of course, the string stretches or something like that. But likely, it's going to be the 1.2 meters, suggesting that the object started that high above the ground. Which also means, though, that we could count on knowing how much potential energy there is, because I'm going to write it as mg. L, the length of the string. At the same time, the object, when it makes it down here, will have kinetic energy, which we can expect to be 1/2 mv squared. So we have a direct method of finding how fast the object's going by using conservation of energy. Now, you might be asking, well, what do I need that for? Because you're specifically being asked for the tension, which suggests that this is a net force equals ma kind of problem or a net force equals 0 problem. Any problem that typically involves finding force usually involves Newton's laws. However, you should all be very aware of which of these two laws is actually in play here. And this is why these problems tend to collect people who make mistakes. Because some people think the tension in the string is just the weight of the box. But that's not true, because you should clearly be able to tell that this object is traveling in a circular path. That's the big indicator. That's the overwhelming thing here, is these problems almost always have a part of the problem where the object is traveling in a circle. And in all problems where an object is traveling in a circle, the net force has to be unbalanced. In fact, because I know some of you are going to make this more confusing than it needs to be, the net force is unbalanced for any object that travels in a circular path or any curved path. So because of that, you should know that the direction towards the center should always be made positive for a successful completion of these questions. But we are starting with the idea that the net force equals MAC, which is point 3. These objects involve uniform circular motion, the centripetal acceleration, meaning there is a relationship that we will use to deal with the acceleration that has to do with velocity. So generally, roller coaster problems have this look about them, and they tend to use conservation of energy to figure out velocity, velocity to figure out the acceleration, and then the acceleration to be used for net force. But remember, these problems can go in any order. I'm asking for the tension. So I'm specifically interested in you being able to figure out the tension, which means starting with net force equals MAC. Recognizing in this problem particularly, the tension is positive because it's towards the center. The object still has weight acting downwards. And this is going to equal mv squared over r. Now there's always a few of you who start getting running on these problems trying to solve them, but we've solved this problem before. We've done this problem before. The thing about review sometimes is it's not just about reminding you about what the problem was about. Sometimes review is also about showing you things that were a little more hidden before, maybe some inefficiencies in your process. What I mean is, if you've already gone ahead thinking that I'm going to ask you to tell me how fast the box is going, understand that you don't actually ever have to figure out how fast the box is going if you're only being asked to determine the tension. Sometimes there are ways around doing a problem that might be easier than they appear. Look, it shouldn't be lost on you that there is a mv squared here. You see it, right? Also, it shouldn't be lost on you that the length is acting as the radius. It seems to me like if you're paying attention, you could maybe do a little bit of algebra and recognize that what you've been given might be able to be used a little different than what we would have done in class before. Meaning, I know that the radius is actually the length. I can replace it there. And I can manipulate this into looking like the centripetal acceleration. This is a lot faster than going through the whole process to find the velocity, which will involve you doing some dividing and taking square roots and stuff, where you invariably say to me, oh, I screwed it up in my calculator. Transferring that number from your calculator back to your paper, using it somewhere else, and then transferring it back to your calculator and then back to your paper several more times, all to find out that the answer was 3 times the weight, 15 newtons. And that I don't necessarily have to figure out how fast I was going. When given numbers, you guys tend to jump to use them, but that's not always the most efficient use of your time. That's the first thing I want to point out. Although all roller coaster problems are inherently the same, and this is what I mean by me saying a roller coaster problem, these problems bring together conservation of energy, net force, and centripetal acceleration. What makes them transition from a problem like this to a roller coaster problem tends to be conditionally having difficulty putting all of this together. So let's talk about the roller coaster problem for a minute. And, well, probably more like 10 minutes. And this will be all we'll do for the rest of the day. Roller coaster problems invariably have conditions associated with them. So I've divided the screen up into two sides because there really are a couple of different ways the physical roller coaster problem tends to be exemplified. The first is the one that is my favorite. When I mean favorite, I mean like my favorite kind of ride. The loop-de-loop ride. I like the ones that go upside down. Always have. They used to scare me when I was a kid, so now I kind of like them. We tend to think of this as a roller coaster problem, and a very straightforward one, in that the car is going to be released someplace on a lift hill and is going to eventually have to travel through the top of the loop. The top of the loop tends to be a point that we talk about a lot. You've seen the questions. They're conditional questions. We'll come back to what I mean by conditional questions. Let's consider the other kind of problem. The other kind of roller coaster problem is a little different in that it tends to have more of a, I don't like that one. Ooh, that's pretty steep. I don't like that one either. I like that one, okay. We don't have one of these in Busch Gardens anymore. They've gotten rid of most of the actual roller coaster wooden platforms, like a twister like this. They tend to go with the ones that go upside down and do loops. But still, the problem is the car is placed here on the top. The ground is located, somewhere around here. And we're interested in what happens to the car when it makes it, to the top of the loop. In this case, it's not a loop. These problems share what I tend to call conditions. They're conditional problems. They tend to have problems that ask questions like, what is the lowest this car can be released and still successfully make it through the loop? Or what is the highest this car can be released and still have a successful trip on top of the hill? These problems are the same as the problem we just looked at, but they place a condition on the problem, a minimum or a maximum that must be met. And that makes these problems infinitely more difficult because, infinitely is a lot. So let's not say infinitely, but let's say maybe several times more difficult. Because when I ask you a question like, what is the maximum height at which I have to start the car or it'll crash in the loop, you might not know even where to begin, even though these problems still involve all of the same things. The car still has gravitational potential energy here. The car is still going to have gravitational and kinetic here, which means the car is going to have a velocity that's related to the energy of the problem. But I can't ignore the fact that, this is a circular motion problem. I can't ignore the fact that the car is 2 times the radius above the ground. But I also can't ignore the fact that the object has 2 forces acting on it. Its own weight and the normal force. And that in this example, those 2 forces act in the same direction, but that doesn't change the fact that the car is traveling in a circle, which means the forces have to be unbalanced. Which is good because they both point in the same direction. They are clearly unbalanced. But that's when it starts to get more interesting. Remember, we're going to make towards the center of the circle positive. And we're going to make sure we recognize that this is still related to the centripetal acceleration. Now, what does it mean to be a condition? Well, the conditional force is the normal force. That's the one that responds to situations. Now look, when I look at this equation, I recognize that once I release the car, the weight of the car doesn't change, the mass of the car doesn't change, and the radius of the hill doesn't change. But I get to decide how fast the car goes. I decide by determining how high I start the car. The higher I start the car, the faster it's going to be going in the loop. which means I get to choose the velocity that the car travels at which the car travels at the top of the loop. If I start it lower, the car's going to go slower. Now that's important because there is a minimum speed. When I look at this, I can get the normal force to increase all I want, but I can't have a normal force that's less than 0. Normal force can't be negative. It can't pull the car down. Pull the car up, which means there's a condition that has to be met. There's a minimum speed, and that minimum exists when the normal force approaches 0. That's what I mean by a conditional problem. It's the same solution. It's the same method of solving it. I'm still going to use conservation of energy, net force, but the moment a condition is placed on it, your understanding of the problem has to increase. Look, we have a conditional over here too. On the other side, there's a radius here. The car is experiencing 2 forces still. Weight downwards and normal force upwards. For it to travel in the circle, they have to be unbalanced. In this one though, mg is the positive direction. It's towards the center of the circle. Minus normal, but the unbalanced force still has to be equal to mv squared over r. Now this problem's a little different. That minus sign definitely makes a change here. Look, the car can go as slow as it wants. It can be stopped there. If it's stopped, then the weight just equals the normal force. It's no big deal. It's not really in circular motion anymore. On the other hand, it is possible for the car to go faster. The car going faster is a problem. In fact, if we just do a little bit of algebra, I just added normal force to both sides and subtracted the unbalanced force from both sides. By doing that, I hope you realize that the normal force, again, is related to V. It can't be negative. It's not holding the car down on the road surface. So I have a condition as this term gets bigger, all of this gets smaller. Well, what's the limit of that? Well, the limit is when the normal force goes to 0, when this term is as big as the weight. That represents the fastest the car can go without requiring a downward force to keep it on the road. If it goes any faster, something has to pull the car down to keep it on the road. If there's nothing to do that, the car jumps. It goes airborne. So these are conditional problems. And although we're not diving into the details too much today, I've outlined what it means to be a conditional problem. They're not going to ask it like this. They're going to say something like, what is the highest you can release the car on track B without having the car leave the track? Or what is the minimum height of the lift hill on track A for the car to successfully make the loop? Those are conditions. They're asking you for the condition in order for a system or a problem to take place. You can write down all the equations, but if you don't understand the conditions, you won't be able to get the answer correct, which is why playing with these conditions are important, and that's what we're going to practice. So, we've reached the end of class. I want you to know that I'm addressing this problem with the video you're going to watch. So make sure you watch the video before class tomorrow, although I'll probably post it this evening. It's about 12, 14 minutes. Make sure you take a little bit of time and watch it. Oops, I lost it.